In 1940, a locomotive rolled out of workshops in Rio de Janeiro that would quietly rewrite the rulebook of steam engineering. European locomotive builders had dominated global railways for nearly a century. Their designs defined what was possible. Their engineers set the standards. Their machines were exported worldwide as symbols of industrial supremacy. Then Brazil built something that made them all go back to their drawing boards. The locomotive was called a Bayer Garrett, but calling it just another Garrett misses the point entirely. What emerged from Brazilian workshops wasn't simply an adaptation of a British design. It was proof that the impossible mathematics of steam power could be solved in ways European engineers had dismissed as unworkable. The numbers alone tell part of the story. These machines developed tractive effort that exceeded anything running on European metals. They hauled loads up mountain grades that would have stalled conventional locomotives. They did it on meter-gauge track, rails spaced just 39 inches apart, the width Europeans considered suitable only for light industrial work or colonial branch lines. The real revelation came when European engineers actually studied what Brazil had achieved. Brazil's railway problem was unique in its brutality. The country needed to move massive tonnages of coffee, ore, and agricultural products from interior plateaus down to coastal ports. The geography was unforgiving. Mountain ranges rose thousands of feet within short distances. Curves snaked through terrain where straight track was impossible. And it all had to run on meter gauge, narrow rails inherited from early construction when capital was scarce, and right-of-way costs mattered more than future capacity. European locomotives struggled in these conditions. Standard designs assumed relatively level routes, gentle curves, and track gauge that provided stability. The powerful express engines that dominated headlines in Britain, Germany, and France were completely wrong for Brazilian service. They were too long, too rigid, too heavy for the track structure. Their weight distribution caused derailments on tight curves. Their fireboxes couldn't generate steam fast enough on sustained mountain climbs. Brazilian engineers needed power, enormous power, but it had to fit within severe constraints. Meter gauge width, sharp curves, light rail, limited maintenance facilities scattered across vast distances. The challenge seemed impossible. The solution came through collaboration with Bayer, Peacock and Company in Manchester, but the critical innovations emerged from Brazilian operating requirements, pushing against British engineering orthodoxy. The Garrett articulated design offered a starting point, a locomotive with the boiler mounted on a separate frame between two powered trucks. This configuration allowed the boiler to swing on curves, while the trucks negotiated the rails independently. Weight distribution improved, curve performance improved, but power remained limited. Brazil pushed harder. The locomotives that resulted weren't simply scaled-up Garretts. Brazilian specifications demanded modifications that British designers initially considered excessive or unnecessary. The fireboxes grew massive, far larger than the boiler diameter would typically allow on a conventional locomotive. The water capacity doubled, then tripled standard tanks. The cylinders increased in both number and bore diameter. Everything about the design maximized sustained power output over long mountain grades. When the first production batch entered service on the Estrada de Ferro Central do Brasil in the early 1940s, the performance data shocked European observers. These locomotives generated tractive effort exceeding 60,000 pounds. On meter-gauge track, they routinely hauled 1,200-ton trains up continuous grades of 2% or steeper. They operated in temperatures ranging from tropical humidity at sea level to mountain cold at high altitude, maintaining consistent performance across environmental extremes. European engineers had assumed such power levels required standard gauge or broader. The physics seemed clear. Narrow gauge meant limited stability, which meant limited weight, which meant limited power. Brazil proved the assumption wrong. The key was weight distribution. Conventional locomotives concentrated weight at specific points, over driving wheels, under the boiler, at the frames. This created stress concentrations that lighter track couldn't handle. The Garrett configuration spread weight more evenly. The articulated design reduced impact forces on curves. The result was a locomotive that could match or exceed the power of much larger standard gauge machines, while operating on infrastructure designed for far lighter loads. The fireboxes demonstrated another breakthrough. On conventional locomotives, firebox size was constrained by the need to fit between the driving wheels and under the boiler. Brazilian Garretts placed the firebox over the rear power truck, freed from these dimensional limits. The great area expanded dramatically. Coal consumption increased, but so did steam generation. The locomotives could maintain full boiler pressure on sustained climbs, where conventional designs would starve for steam and lose power. Water capacity solved another critical problem. Mountain grades meant extended periods at maximum output. Steam consumption soared. Conventional locomotives ran out of water and had to stop for refilling, sometimes multiple times on a single climb. The Brazilian Garretts carried water in massive tanks mounted on both power trucks, extending range between stops and maintaining schedule reliability. European locomotive works took notice. Reports circulated through engineering journals. Photographs appeared showing these machines hauling trains that shouldn't have been possible on such narrow gauge. Performance data was analyzed, questioned, then verified through independent observation. The conclusions were unavoidable. Brazil had developed steam locomotives that exceeded European designs in specific but critical performance metrics. The redesign process began quietly. British manufacturers modified their standard Garrett specifications. The German builders reconsidered weight distribution in their own articulated designs. French engineers studied the Brazilian firebox arrangements. The changes weren't wholesale revolutions. Steam locomotive design had evolved over a century, and fundamental principles remained constant. But the details shifted. Assumptions were questioned. New configurations were tested. The influence spread beyond Garrett's. Conventional locomotive designs incorporated lessons from Brazilian service. Firebox sizing increased. Water capacity expanded. Weight distribution received more careful analysis. The changes were incremental, often unacknowledged, but they represented a fundamental shift. European engineers were learning from colonial railways, from machines operating in conditions they dismissed as marginal or temporary. South African railways adopted Brazilian-influenced Garretts for their own mountain operations. Australian systems ordered similar designs. Even operations in Wales and Scotland, facing terrain challenges within Europe itself, specified locomotives incorporating features pioneered under Brazilian requirements. The technology transfer ran backward, from periphery to center, from necessity to refinement. The irony deepens when you consider the timeline. These developments occurred as European industry faced wartime disruption and resource constraints. Brazilian workshops, distant from the conflict, continued refining and producing locomotives that set new performance benchmarks. When peace returned and European manufacturers resumed normal production, they built machines incorporating Brazilian innovations. Yet the story never entered popular history. Railway enthusiasts celebrate British Pacifics, German streamliners, French compounds. The great locomotives of legend ran on standard gauge over relatively gentle terrain, hauling passenger expresses at high speed. They made headlines. They appeared in films. They defined public imagination about steam power. The Brazilian garrets worked in obscurity. They hauled freight through mountains. They broke records nobody publicized. They solved problems most observers didn't realize existed. And when steam gave way to diesel, they were scrapped without ceremony or preservation. A handful survive in museums, mostly forgotten except by specialists. The engineering legacy persists in subtle ways. Modern locomotive design still reflects lessons learned from those meter-gauge monsters. Weight distribution principles, articulation strategies, power output optimization, these technical advances influence development paths that led to contemporary designs. The connection isn't direct or linear, but it exists in the accumulated knowledge of how to build powerful, reliable machines for difficult service. The broader lesson cuts deeper than locomotive specifications. Innovation doesn't flow only from industrial centers to peripheries. Necessity drives development in unexpected places. Operating requirements that seem marginal or specialized can produce solutions with universal application. The engineers who designed the Brazilian garrets weren't trying to revolutionize European practice. They were solving immediate, practical problems with the constraints and resources available. The fact that their solutions proved superior in certain metrics wasn't the goal. It was the byproduct of focused, disciplined engineering. History remembers what captures public imagination, not necessarily what advances the technical state of the art. The Brazilian garrets were objectively remarkable machines. They remain obscure because they operated outside the spotlight, serving economic functions rather than representing national prestige or engineering showpieces. They were tools that worked, brutally effective, and thoroughly unglamorous, which raises a question worth considering. How many other forgotten achievements lie buried in industrial archives, overlooked because they emerged from the wrong place, served the wrong market, or simply worked too well to generate drama? The locomotives that made European engineers redesign everything are nearly forgotten. What else has history missed while celebrating the famous?